welcome to EC BTech, your guide for BTech and beyond. My name is B. Manohar. Today's the topic is filters from the electronic devices and circuits subject. Now why we are using the filters? Moreover, all electronic devices works under DC supply. If we give an AC voltage, due to the fluctuations, all the devices can get damages. Okay, to overcome that problem, all the electronic devices are worked under the DC supply. For the conversion of AC to DC, we use some power supply sections. In the previous lectures, we have studied the first stage is a transformer which converts 230 of AC to 9 volts or 12 volts or 5 volts of AC. This voltage rating can be done using a mutual induced transformer. Then after we are having a rectifier which converts AC to pulsating DC. Then we will be having filters. For smoothing purpose we are using the filters. Filters are used to remove unwanted AC portion. Unwanted AC portion are ripples presented in the output of rectifier. Then we have a regulated session. Okay, in the today's lecture, what is the ripple factor of a filter? We are going to find it. Okay, students, we will start the session. Filters. It is used to remove unwanted AC portions, unwanted AC portion present in the output of rectifiers. Output of rectifier. Suppose you can take it is an AC, it is a rectifier. Output of a rectifier is both IDC plus IAC. Okay. This filter section is used to remove an AC portion. This AC portion can be removed using these filters. Like that, in the session we have classified different types of filters. There, the first one is induction filter. Or we'll call it as a series filter. Or second, capacitor filter. Or shunt filter. Next, L section filter. This we'll call as a LC filter. Next, pi section filter. This we'll call as a CLC filter. These are the filters we are using here. Okay, students, listen. The first, it is used to remove unwanted AC portion presented in the output of rectifier. Now, because output of in rectifier, we have both AC and DC portion. Now, to get a DC output, we have to neglect an AC portion. These are the various ways for removing AC. AC portions. removing AC portions. Okay, students, this we will discuss in detail about all this filter section. Now, first, initially, we will see what is induction filter. Induction filter. In an induction filter, inductor and load resistance or load are connected in series. Okay, inductor and load are connected in series. That is why it is called as a induction. That is why it is called as a series filter. Okay, the construction of inductor and load are connected in series to the rectifier. That is why we will call it as a series filter. Okay, now here for AC portion, reactance of inductor is high. For AC portion, reactance of inductor is high. Okay, and you can remember the point, the fundamental principle of inductor is it does not allow sudden change in the current, sudden changes in the current. Okay, now you can see the construction. This is a rectifier section. This is a rectifier. Here we are connecting a inductor, or we'll call it as a choke. Here the load connected. Here input. That is the ripples we will write V out is equal to output VAC plus VDC, an output of a rectifier. Now you can see here both L and R are connected in series. Both L and R connected in series. That is why it is known as an series filter. Now what you can see, inductor blocks AC portion and allows DC portion. Now if you see an reactance of an inductor, XL is equal to J omega L, or simply we'll write, if you apply mod omega L, we will write 2 pi Fn. We know for DC signal, F is 0, XL is equal to 0 into 0. Means reactance is 0. Reactance is, inductive reactance is 0 for DC signal. Inductive reactance is 0 for DC portion. Then inductor allows DC. It acts as short circuit. For example, XL is equal to, for an AC, 2 pi, if F is like 50 into L, Henry some value, like 5 millihenry. Like that you can possess some reactance because frequency is present. Then reactance increases. As reactance increases, high reactance for AC signal. Then inductor blocks AC signal. Allows DC signal. Inductor blocks AC signal and allows DC signal. Now you can see in the previous lecture, now what happens, whatever here portion, output of rectifier, we are having AC portion and DC portion. Now this inductor will block DC, inductor blocks AC, and whatever the DC portion is there, it allows DC, and the full DC can appears across the RL. Full DC will appears across the RL. That is why. Now what you can understand here, inductor blocks AC signal, allows DC. Okay, output of rectifier portion consists of AC as well as DC. But inductor blocks AC and allows DC signal. Across RL, DC is present. DC signal is present. Okay, in this way, using inductor filter or using a series filter, we will block AC portion and we will allow DC portion to reach the load. Is one of the way for filtering. Means AC portion blocking purpose we use this inductor filter, and similarly we will call it as a this we will call as a series filter or inductor filter. Now if you see, if you calculate a ripple factor for this, what is the ripple factor? IRMS by IDC. IRMS by IDC. Now you can remember this is the case VDC plus VAC. Inductor, load resistance R. Apply a KVL. This is R. The structure inductor. Now if you want to write, if you calculate ripple factor, we know IDC. IDC is equal to the ripples here, ripple voltage that is 2 Vm by pi minus 4 Vm by pi into cos 2 omega t by 3 plus cos 4 omega t by 15 plus cos 6 omega t by 34 plus so on. Okay, these are expressions. What you can see here, from this we will take it is a component. We may took the output voltage. IDC is equal to, we will write a 2 Im by pi for full wave rectifier. What is the average value? IDC is equal to 2 Im by pi, where we have studied in the last class. Now we will write here ripple factor is equal to okay students, IDC, we will write IDC is equal to from the Ohm's law VDC by RL. Now we know what is VDC. VDC is nothing but 2 into Im by Vm by pi into RL. We might this IDC in terms of Vm, we will write IDC is equal to 2 Vm by pi RL. Because here IDC is equal to VDC by RL. VDC is nothing but 2 Vm by pi into RL. We will get this expression. Similarly, IRMS is equal to, we write as Im by root 2. Similarly, IRMS is nothing but Im by root 2. If we want to write this in terms of voltage, VRMS, we may write the similar manner. IRMS is equal to VRMS by RL. VRMS, because it is an AC. IRMS is nothing but IAC. And you remember in an inductor filter, due to this filter, it has during the AC portion, you have the both inductance. This reactance of inductor and a load. We may choose this is XL. And in an inductor filter, the choosing of an inductor and load, it should be in this choosing of an inductor, that is reactance of an inductor is far greater than RL. Reactance of an inductor is far greater than RL. Like that you have to choose that reactance of an inductor. Now from this we will write VRMS by RL. RL is nothing but XL, because for an AC portion. Now IAC is equal to VRMS, means Vm by root 2 into XL. Therefore, for full wave rectifier, we will write XL is equal to 2 omega naught L. For half wave rectifier, we may choose XL is equal to omega naught L. This is for half wave rectifier. This is for full wave rectifier. is the output of DC portion. Okay, simple students, to calculate the ripple factor for inductive filters, IRMS by IDC, that is a RMS value of RMS value of to the average value is a ripple factor. Now we will calculate in this manner. Now from this we will write Vm by root 2 into XL. Now we will write in place of what is the Vm value? This is the Vm value. We will write IAC is equal to Vm means 4 Vm by 3 pi, because if you make here 3, 15, 35, if you take 3 common, here 1, here 5, here 6, 6, 5, if you take a 3 common, is it clear? Now we will write 4 Vm by 3 pi, this Vm value is 4 Vm by 3 pi into 1 by root 2 into XL, 1 by XL. Okay students, we will see in the next slide. Now we will write IAC or IRMS is equal to 1 by root 2, 4 Vm by 3 pi into 1 by XL means 2 omega naught L. This is the structure. Okay students, now we will write this is a IAC. IDC is 2 Vm by pi into RL. To calculate the ripple factor, we will write IRMS, that is 1 by root 2 into 4 Vm by 3 pi into 1 by 2 omega naught L by this value, IDC value, that is 2 Vm by pi into RL. Okay, now from this Vm will cancel, 2 1s, 2 2s. Is it clear? Here 2 will get cancelled, and here pi will get cancelled. Okay students, what terms we are having now? This RL will goes up. This we will write as RL by 3 root 2 omega naught L. The ripple factor, this is a ripple factor for inductor filter. This is a ripple factor for inductor filter. Now you can write for inductor filter, ripple factor is, for inductor filter, ripple factor is directly proportional to the load. Okay, for the inductor filter, ripple factor is directly proportional to the load. Remember, this is RL by 3 root 2 omega naught L. Okay students, this is the inductor filter ripple factor. Suppose in examination he may ask the similar problems. We will discuss in one session as a problem descriptions. Next we will see capacitor filter. This also we'll see. It is a rectifier. Is connected to here the capacitors are connected in series. Sorry, capacitors are connected in parallel, C, and load resistance. Students, you can see the capacitor is connected in parallel to the rectifier. Now output of rectifier the same, we have IDC plus IAC. Output of rectifier, we have both AC component and DC component. What does the capacitor behavior? The fundamental, okay. The fundamental principle of capacitor is it does not allow sudden change in current, sudden changes in the voltage, okay. For an inductor, it does not allow sudden change in the current. Similarly, in the capacitor behavior, fundamental behavior is it does not allow sudden change in the voltage. Now, if you see the reactance of an inductor, in this selection, you can select this. Reactance of capacitor must be smaller than that of or less than that of the load. We have to choose capacitor reactance must be reactance of the capacitor for an AC portion must be smaller than that of or less than that of load resistance. Okay, now you can see what does the capacitor does. When AC is applied, okay, now what you can say, Xc is equal to 1 by j omega c. For mod, you write 1 by omega c, that is 1 by 2 pi fc. Now 1 by value, 1 by this value, 1 by like a frequency like 50 into 2 pi into c. Now this value is larger. Now what I can say, this is larger means this is smaller. This is reactance, this is capacitor. If it is greater, then reactance is smaller. Those both are inversely proportional. That is for high frequency, capacitor can act as a short circuit. That is why capacitor allows AC. Okay. See here, capacitor allows AC signal or portion, because for AC, capacitor act as short circuit. Now similarly for DC, you can see for DC signal, Xc is equal to 1 by omega c, that is 1 by 2 pi. Frequency for this is 0, 1 by 0 is infinity. Reactance is infinity. Capacitive reactance is infinity for DC signal. Then reactance is what you can understand here, capacitor act as open circuit for DC signal. AC signal means it blocks DC. It blocks DC. Now you can see output you are having, output of rectifier you are having DC portion and AC portion. Whatever the AC portion is there, that AC portion completely stored in the capacitor, and whatever the DC is there, because DC does not allow it pass. Now whatever the DC signal is there, that DC signal can fully appear across the load resistance. The DC signal will fully appear across the load resistance. Okay, signal. Output of rectifier contains both AC and DC output, but capacitor blocks DC. Capacitor blocks DC signal and allows AC signal. DC signal is fully occupied across the load resistance RL. Okay, that depends upon the time constant. We will see. Suppose if we are taking a half wave rectifier, for a half wave rectifier, okay. This is an half wave rectifier. Is an half wave rectifier 0 to pi, pi to pi, 3 pi. It means during positive half cycle it can allow. During the negative half cycle it does not allow. And during the positive half cycle it allows for the half wave rectifier. We have studied in the previous lectures. Okay. Now what happens? What does the capacitor will does? It is a peak amplitude. It is a PM. Now, up to this portion, this we assume as okay. This 0, this time interval will be represented at 0 T1, it is T2, it is T3. Now you can see this time interval. Capacitor will charge. Capacitor, this output you are giving to the output of this rectifier you are giving to filter. Okay, capacitor will charge. Capacitor will charge up to peak value. Capacitor will charge up to this peak value Vm. Okay. Next, due to in this we are having this a capacitor and load resistance. This is a discharging path of the capacitor. Now it is a time constant. Tau is equal to RC. Now what happens? RC value. Now the discharging path of the capacitor and the time constant value tau is equal to RC. Now this value tau is larger. When this value is larger, slowly discharging. Now from this point to this point the capacitor will charges fully. After this the capacitor will slowly discharges up to this point. Again when next input is again greater, again it starts charging up to its peak time. Capacitor starts charging. Okay. Now it is a slowly discharging path. Due to these parameters, time constant. Okay. Now what I can say? Now this unwanted portion is there now. It is allowing. Now it is in a triangular form. The output is like a capacitor will charge up to peak value. Okay. Due to capacitor does not allow sudden change. Sudden change in voltage. Sudden changes in voltage due to time constant. Discharging path of the capacitor is slower. Okay. Then we will get a ripple factor for an half-wave rectifier. The ripple factor for capacitive filter is 1 by 2 root 3 F naught C RL. This is the ripple factor for half-wave rectifier. Suppose you can take a full wave rectifier. For this, capacitor will charge up to this maximum peak point, then it slowly discharges, slowly discharges. Means rectifier output is in this manner. After rectifier output we apply to filter, and filter output is a triangular wave. And a ripple, and RMS value of triangular wave is Vm by root 3. RMS value, remember, The triangular wave is Vm by root 3 value. And full wave rectified, the ripple factor is 1 by 4 root 3 F naught C RL. This is for capacitor filter. So this is a construction. Rectifier. Simple here, the capacitor, you are aligned capacitor. Capacitor blocks DC, allows AC. Whatever the AC portion is there, whole AC can occupied across the capacitor. And whatever the DC is there, DC will go through and appears across the load resistance. In that way, it is it can efficient. It means we can remove more amount of AC portion and maximum of DC can appear across the load. It is better than that of inductive filter. Capacitor filter is also known as shunt filter. Why we will call it is a shunt filter? Because capacitor is connected in parallel to the load resistance. Inductor is connected in series. That is why it is known as series filter. It is connected in shunt. So it is known as it is connected in shunt. That is why it is known as a shunt filter. And voltage across current division. Same if you take an inductor in series, current division will be same and voltage division can be takes place. But whereas in parallel node voltages are same. Okay, students, this is about capacitive filters. Now we will discuss about L section filter. L section filter. Okay, for better removal of a ripple factors are we use these filters. See, it is a rectifier. We combine both series and shunt filter. We are connected inductor and we are connected a capacitor, LC. Here you are connecting a load, RL. Okay, now you can say you are having AC plus DC. Now you can say inductor blocks AC, means some AC is blocked here, and after that whatever the AC, if any AC component is arrived, that can be blocked across the capacitor and the whole DC will appear across the load. Means in first stage inductor blocks AC portion, not perfectly blocked. Okay, simple. In first stage, inductor blocks AC portion, allows a DC signal. In second stage, capacitor allows AC signal. Now the total AC portion is minimized. Total AC portion is minimized. Okay, maximum DC will appear across the load resistor. load resistor. Okay, students, you can see this is a L section filter. Same how the inductor and the capacitor principles here. In such a way that we will get the ripple factor root 2 by 3 XC by XL. This is the ripple factor for L section filter or LC filter. LC filter. Okay, students, we go for the next, that is pi section filter. Pi section filter. In this pi section filter, we have same rectifier, here we are having capacitor, we have here okay, this is a pi section filter. It's a pi section filter. Now you can see here clearly. During this, you have the first stage, capacitor, inductor and capacitor. This a better purification can be done, better removal of AC can be done here. Now, moreover, we are using the filter is to remove the ripple factor, to remove the ripples, means AC. What are the ripples? Whatever the AC portion is present, that we will call as a ripple. Now, here we use first stage is second stage and third stage. In the first stage, what does the capacitor will does? Capacitor will block DC. Capacitor will block DC and allows AC. Whatever the output of DC, output of rectifier, AC portion is there. All the AC portion or AC value can be occupied in this capacitor. Capacitor stores that value, and the DC can allow by the inductor. Inductor can act as a short circuit for a DC supply, and if any low portion of AC is passed, this third stage of capacitor can completely blocks the DC signal, and whatever the AC portion is there, that whole AC portion can occupied in this capacitor. Okay, we have the three stage. First stage, this capacitor allows AC or AC portion is stored in this capacitor. Okay, second stage, inductor allows DC to pass. Next, third portion. If any chances AC presents, AC will stored in capacitor. Okay. Full DC will appear. Full DC signal will appear across the load resistance. This is a perfect. Okay. Moreover, DC is completely gated output. Maximum of DC signal is occupied and maximum of AC portion is suppressed using this pi section filter because of various stages. Okay. Now this ripple factor for this is root 2 by RL XC XC1 by XL. This is the ripple factor for pi section filter. Ripple factor for pi section filter. Okay, it is widely used. So you will see the comparison. First, L filter, C filter, LC filter, that is L section filter, pi section filter. Okay, students. Okay, students, you can see L section filter, single inductor, here single capacitor, here single inductor and capacitor, both we are using. Here we are using C, capacitors 2, inductor 1. Okay. More accurate, less accurate, medium. It is also good. Okay, if you use the ripple factors, this is RL by 3 root 2 omega naught L. But this is for full wave rectifier. We use 1 by 4 root 3 F naught C RL. For this is root 2 by 3 XC by XL, root 2 by RL, XC, XC1 by XL. Okay, students, this is about inductor and capacitor and L section and pi section filters. Students, In this today's lecture, we have studied what are the filters and what are the importance of filters and what are the ripple factors of these filters. Okay, you can remember only one point. Filters are used to remove AC portion presented in the output of rectifier, because for an electronic devices we need only DC supply. DC supply is needed and AC is subtracted, means removed.